Imagine a world where the familiar rules of physics fade away, replaced by something altogether stranger and more captivating. This is the realm of quantum physics, a branch of science that studies the bizarre behavior of matter and energy at the atomic and subatomic levels. From the smallest particles to the largest stars, quantum physics governs it all. Get ready to have your mind blown wide open as we explore the captivating world of quantum physics, a world where the only constant is uncertainty and the possibilities are truly limitless. To understand why quantum physics is so groundbreaking, we need to shrink ourselves down to the size of an atom. In this microscopic world, the laws of classical physics simply don't apply. Here, a whole new set of rules takes over, and the behavior of particles becomes utterly unpredictable. Instead of knowing for certain where an electron is, we can only calculate the probability of finding it in a particular location. This probabilistic nature of the quantum world challenges our intuitive understanding of reality. You might be wondering, if quantum physics is all about the microscopic world of atoms and particles, why should we care? The answer is simple. Quantum physics is far from just a theoretical curiosity confined to laboratories. Take, for example, the smartphone you might be reading this on. The transistors that power your phone's processor, the lasers that read the data on your CDs and DVDs, even the LED lights illuminating your screen, all rely on the principles of quantum physics. Techniques like magnetic resonance imaging, MRI, use the quantum properties of atoms to create detailed images of the inside of the human body. From the devices we use every day to the cutting-edge technologies of tomorrow, quantum physics is shaping our world in profound and often invisible ways. Quantum physics challenges our very understanding of reality. It tells us that the universe is not a collection of solid objects interacting in a predictable way, but rather a dynamic web of possibilities. This inherent uncertainty might seem unsettling at first, but it's also incredibly liberating. It suggests a universe far stranger and more wondrous than we ever imagined, filled with potential and open to possibilities we are only just beginning to explore. Our journey into the quantum realm begins at the dawn of the 20th century with a German physicist named Max Planck. Planck was grappling with a problem that had baffled scientists for years: the nature of black-body radiation. Planck's groundbreaking solution, proposed in 1900, was to suggest that energy is not continuous, but rather comes in discrete packets, or quanta. He introduced a fundamental constant now known as Planck's constant, which relates the energy of a quantum of radiation to its frequency. This revolutionary idea that energy is quantized marked the birth of quantum physics. Five years after Planck's revolutionary idea, a young Albert Einstein would take the concept of quantized energy and apply it to one of the most fundamental mysteries in physics: the nature of light. Einstein proposed that light itself is quantized, consisting of discrete packets of energy called photons. He explained the photoelectric effect, where light shining on a metal surface can eject electrons, by suggesting that each photon interacts with a single electron. Einstein's work on the photoelectric effect solidified the concept of quantized energy and cemented the importance of quantum physics in understanding the nature of light and its interactions with matter. While Planck and Einstein were revolutionizing our understanding of light and energy, another physicist, Niels Bohr, was applying quantum principles to unravel the mysteries of the atom itself. Bohr, in 1913, proposed a radical new model of the atom, incorporating quantum principles. He postulated that electrons can only occupy specific discrete energy levels or orbits around the nucleus. Bohr further proposed that electrons can jump between these energy levels by absorbing or emitting photons of specific energies. This explained the discrete spectral lines observed when light is emitted or absorbed by atoms, a phenomenon that classical physics couldn't account for. As the 1920s unfolded, the field of quantum physics witnessed an explosion of theoretical advancements. Heisenberg's famous uncertainty principle states that it is impossible to simultaneously know with perfect accuracy both the position and momentum of a particle. Schrödinger's wave equation describes the behavior of particles in terms of wave functions, providing information about the probability of finding a particle in a particular state. These brilliant minds and others continued to develop and refine the theoretical framework of quantum physics, leading to a deeper understanding of the nature of matter, energy, and the fundamental laws governing the universe. The first few decades of the 20th century witnessed a period of intense theoretical development in quantum physics. One of the most widely accepted interpretations is the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg. The Copenhagen interpretation emphasizes the probabilistic nature of quantum mechanics, stating that we can only predict the probabilities of various outcomes in a quantum system. Another interpretation, the many worlds interpretation, suggests that every quantum measurement causes the universe to split into multiple parallel universes. Despite the various interpretations and ongoing debates, the mathematical framework of quantum mechanics has proven to be remarkably successful in explaining a wide range of phenomena. For centuries, scientists grappled with a fundamental question about the nature of light. Is it a wave, rippling through space like waves on a pond? Or is it a stream of particles, tiny packets of energy hurtling through the cosmos? Turns out, light is both. It can act like a wave, exhibiting properties like diffraction and interference, bending around obstacles and creating patterns of light and shadow. Yet it can also behave like a particle, carrying discrete amounts of energy and momentum as demonstrated by the photoelectric effect. Imagine a beam of light passing through two narrow slits. If light was solely a wave, we'd expect to see an interference pattern on a screen behind the slits. But here's where it gets strange. If we send through one photon at a time, we still see the interference pattern build up gradually, even though each photon should only pass through one slit. If light, something we typically think of as a wave, can also behave like a particle, could the reverse be true? Could matter, the stuff we're made of, also exhibit wave-like properties? In 1924, a French physicist named Louis de Broglie boldly proposed just that. He suggested that just as light has a wave-like nature, particles of matter like electrons should also have a corresponding wavelength. De Broglie's hypothesis was experimentally confirmed a few years later when electrons were observed to diffract or bend, just like waves when passing through a crystal. Imagine a tiny sandbox, far smaller than the width of a human hair, where the rules of our everyday world cease to apply. This is the realm of the quantum, where particles dance to a different tune, governed by probabilities and uncertainties. In this strange and wonderful domain, particles don't behave like tiny billiard balls, following predictable paths. Instead, they exist as blurry clouds of possibilities, their locations and properties described by wave functions, mathematical expressions that encode the probabilities of finding a particle in a particular state. One of the most mind-boggling aspects of the quantum world is the concept of superposition. Imagine a coin spinning in the air, not yet landed on heads or tails. In the quantum sandbox, a particle can exist in a superposition of states, much like that spinning coin, simultaneously embodying multiple possibilities until we measure it. It's as if an electron could be in multiple places at once, or spinning both clockwise and counterclockwise simultaneously. This isn't just a theoretical quirk, it has real observable consequences. For example, the superposition of energy levels in atoms is what gives rise to the distinct colors emitted by different elements when heated. Section 4. Uncertainty, the price of knowledge in the quantum world. In our everyday lives, we take it for granted that we can observe something without influencing it. Look at a parked car and it remains unmoved. But in the quantum sandbox, the act of observation takes on a whole new meaning. Heisenberg's uncertainty principle, one of the cornerstones of quantum mechanics, tells us that the more precisely we try to measure one property of a particle, like its position, the less precisely we can know another property, like its momentum. It's not a matter of our instruments being imprecise, it's a fundamental limit imposed by nature itself. Imagine trying to pinpoint the location of a tiny, fast-moving particle. The very act of shining light on it to observe it imparts momentum to the particle, altering its course in an unpredictable way. The more precisely we try to determine its location, the more we disturb its momentum, and vice versa. This inherent uncertainty is not a sign of our ignorance, but rather a fundamental feature of the quantum world, reflecting the wave-like nature of matter and the probabilistic nature of quantum mechanics. One of the most mind-bending concepts in quantum physics is superposition, the idea that a quantum system can exist in multiple states at once until measured. Imagine an acrobat balancing on a high wire, but instead of being in one position at a time, they're somehow spread out along the entire wire, simultaneously in every possible position. That's the essence of superposition. A quantum particle, like an electron, doesn't have a definite location until we measure it. Before measurement, it's in a blurry state, a superposition of all possible locations, like a ghostly echo spread throughout space. It's only when we try to pin down its location that the superposition collapses and the particle chooses a specific position. This isn't just theoretical whimsy, it has real-world consequences. Superposition is what allows quantum computers to perform calculations in parallel, exploring multiple possibilities simultaneously, giving them an exponential speed advantage over classical computers for certain types of problems. Think of a maze. A classical computer would have to try each path one by one until it found the exit. A quantum computer, thanks to superposition, could explore all paths simultaneously, finding the solution much faster. Erwin Schrödinger, one of the pioneers of quantum mechanics, devised a famous thought experiment to illustrate the paradoxical nature of superposition. Imagine a cat sealed inside a box with a diabolical contraption. The contraption contains a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers, releasing the poison, and the cat tragically meets its demise. Here's the quantum twist. The decay of the atom is a probabilistic event governed by the laws of quantum mechanics. Until we open the box to observe the cat, the atom exists in a superposition of having decayed and not decayed. This means the cat is also in a superposition, both alive and dead simultaneously, a macabre quantum tango. Schrödinger's cat isn't meant to be taken literally. It's a thought experiment designed to highlight the strangeness of applying quantum superposition to macroscopic objects. It forces us to confront the limits of our classical intuition when dealing with the quantum world. The act of observation, of opening the box, collapses the superposition, forcing the atom to choose whether or not to decay and determining the fate of the unfortunate feline. If superposition is the quantum acrobat, then entanglement is the quantum magician, capable of feats that defy our classical understanding of space and time. Imagine two particles born together in a quantum process, forever linked in a way that transcends distance. These entangled particles share a special bond, a quantum connection that ensures that even if separated by vast distances, their fates remain intertwined. Measure the state of one particle and instantly you know the state of the other, no matter how far apart they are. It's as if flipping a coin on Earth could instantly determine the outcome of a coin flip on a distant star. Einstein famously called this spooky action at a distance because it seemed to violate his theory of special relativity, which prohibits information from traveling faster than the speed of light. However, entanglement doesn't actually allow for faster-than-light communication. While the correlation between entangled particles is instantaneous, the information gained from measuring one particle doesn't reveal anything about the other until that information is classically communicated, which is still limited by the speed of light. Entanglement is one of the most profound and mysterious phenomena in quantum physics, with potential applications in quantum computing, cryptography, and teleportation. Section 4, quantum tunneling through walls and beyond. Imagine throwing a tennis ball at a wall. In our classical world, it bounces back, thwarted by the solid barrier. But in the quantum sandbox, the rules are different. A quantum particle, like an electron, has a chance of tunneling through the wall, appearing on the other side as if by magic. This isn't just theoretical. Quantum tunneling is a real phenomenon with practical applications. It's why the sun shines, allowing protons to overcome the electrostatic repulsion of their like charges and fuse in the sun's core, releasing energy. Quantum tunneling is also crucial for technologies like transistors, the building blocks of modern electronics. In a transistor, electrons tunnel through thin insulating layers, controlling the flow of current and enabling our digital world. The probability of tunneling depends on the particle's energy and the width of the barrier. The higher the energy and the thinner the barrier, the more likely tunneling becomes. Think of it like rolling a boulder uphill. A small boulder might tunnel through a thin barrier, while a larger boulder would need more energy to have any chance of success. Section 5. Quantum fields, the universe's deep symphony. To appreciate quantum physics, we must embrace quantum fields. Imagine the universe as a vast ocean of quantum fields. These fields are the fabric of reality. Particles are like ripples on this quantum ocean. Waves can interfere, creating patterns just like quantum fields. The electromagnetic force is mediated by the photon field. The strong force is mediated by the gluon field. Quantum field theory combines quantum mechanics with special relativity. It provides a framework for understanding matter and forces, a symphony of fields creating the tapestry of reality. Quantum technologies shaping the future. Quantum physics began as theoretical but is now revolutionizing technology. Scientists harness quantum mechanics for groundbreaking technologies. Quantum computers solve problems impossible for classical computers, transforming medicine, materials science, telecommunications and AI, leveraging superposition, entanglement and quantum tunneling. A technological revolution driven by quantum physics. Section 2. Quantum computers. Beyond bits and bytes. In the digital age, computers have become indispensable tools, processing information, solving problems, and connecting us in ways unimaginable just a few decades ago. However, even the most powerful classical computers, based on the manipulation of bits, which can represent either a 0 or a 1, face limitations when it comes to tackling certain types of problems. This is where quantum computers, the rock stars of the quantum realm, step onto the stage. Instead of bits, quantum computers employ qubits, which can exist in a superposition of 0 and 1 simultaneously, thanks to the mind-bending principles of quantum mechanics. This allows quantum computers to perform computations on multiple possible values at once, giving them an exponential speed advantage over classical computers for specific types of problems. Imagine searching for a single needle in a haystack the size of Mount Everest. A classical computer would have to meticulously examine each piece of hay one by one until it stumbled upon the needle. A quantum computer, on the other hand, could analyze all the haze simultaneously, drastically reducing the search time. Quantum computers are particularly adept at solving problems related to optimization, simulation, and cryptography. Section 3. Quantum Cryptography, Unbreakable Secrets. In an age of ever-increasing data breaches and cyber attacks, the need for secure communication has never been greater. Governments, businesses, and individuals alike rely on encryption to protect sensitive information from prying eyes. But even the most sophisticated classical encryption methods can be vulnerable to attacks from hackers and eavesdroppers. Enter quantum cryptography, a revolutionary approach to secure communication that leverages the principles of quantum mechanics to create virtually unbreakable encryption keys. Quantum cryptography exploits the unique properties of quantum systems, such as the no-cloning theorem and the sensitivity of entangled particles to measurement, to ensure that any attempt to intercept or eavesdrop on a communication is immediately detectable. Imagine sending a message written in invisible ink that changes color if someone tries to read it without authorization. Quantum cryptography provides a similar level of tamper-evident security, making it virtually impossible for eavesdroppers to intercept messages without being detected. While still in its early stages of development, quantum cryptography holds the promise of revolutionizing cybersecurity, providing a new level of protection for sensitive data in an increasingly interconnected world. Section 4. Quantum Biology, Life's Quantum Secrets. Quantum physics was once only for inanimate matter, but now it might influence life itself. Quantum biology explores how phenomena like superposition and entanglement affect biological processes. Photosynthesis may rely on quantum coherence for efficient energy transfer. Migratory birds might use a quantum compass to navigate. Quantum biology could revolutionize our understanding of life and the universe. The quantum frontier, mysteries yet to unfold. Quantum physics remains a realm of profound mystery and wonder, a frontier of knowledge. Despite its success, it grapples with the biggest questions in science. What is the nature of quantum gravity? How does measurement collapse the wave function? What are the implications for consciousness and reality? These questions challenge and inspire curious minds. The journey into the quantum realm has only just begun. The Quantum Legacy, a century of awe and wonder. Over the past century, quantum physics has emerged as one of the most transformative scientific revolutions in human history, profoundly altering our understanding of the universe and paving the way for technological advancements that have reshaped our world. From the humble beginnings of Max Planck's quanta to the mind-bending concepts of superposition, entanglement, and quantum fields, our journey through the quantum realm has been nothing short of awe-inspiring. We've encountered a universe stranger and more wondrous than we ever imagined. A universe where particles can exist in multiple states at once, where information seems to travel faster than the speed of light, and where the very act of observation can influence the outcome of an experiment. Along the way, we've met the brilliant minds who dared to challenge the classical worldview. Pioneers like Einstein, Bohr, Heisenberg, Schrödinger, and Dirac, who pieced together the enigmatic puzzle of the quantum, often grappling with paradoxes and uncertainties that defied common sense. Their legacy is a testament to the power of human curiosity, our relentless pursuit of knowledge, and our ability to embrace the unknown, even when it challenges our most cherished assumptions about the nature of reality itself. The universe in a grain of sand, quantum physics, and our place in the cosmos. Quantum physics is the fundamental language of the cosmos, shaping the universe we inhabit, from the smallest atoms to the largest stars, to the intricate dance of molecules in our bodies. Quantum phenomena orchestrate the symphony of existence. The same quantum processes drive the fusion reactions in stars, releasing the energy that bathes our planet in light and warmth. Quantum physics has given us tools to explore the universe, revealing distant galaxies and the remnants of the Big Bang. We gain a deeper appreciation for the interconnectedness of all things. Embracing the quantum unknown, a future of limitless possibilities. The future shimmers with potential, ripe with opportunities to harness quantum mechanics to solve humanity's greatest challenges. Quantum computers promise to revolutionize medicine, material science and AI, leading to new drugs, innovative materials and advanced algorithms. Quantum cryptography offers unbreakable encryption, safeguarding our data. Quantum sensors could revolutionize medical imaging, environmental monitoring and navigation. Quantum biology hints at breakthroughs in health, disease and consciousness.